Somewhere in your kitchen, there is an orange, or the memory of one. Peel it in one long unbroken piece. Now press that peel down against the table and make it lie flat. It will not. It buckles, and then it splits. And no matter how gently you work, some part of it has to tear. That small stubbornness is the reason no flat map of the world has ever told the truth. Greenland swells up like a continent. Africa quietly shrinks. Every map you have ever looked at is that torn peel arranged politely. For 2,000 years, geometry meant the flat page. Straight lines, tidy triangles, corners that always added up to the same dependable number. However, the flat page turned out to be the unusual case rather than the rule. Curved surfaces are ordinary. Flatness is the rarity, and space itself, as far as anyone has been able to measure, never promised to be flat at all. Tonight, we follow that one idea slowly, all the way from the beginning. From people standing barefoot in Nile mud with knotted rope, laying out fields the flood had washed away, through a single sentence about parallel lines that kept careful minds awake for 20 centuries, through painters and ants, and a young man's lecture that almost nobody in the room understood, until the day the shape of gravity fell out of it. You do not have to remember any of this. You are welcome to fall asleep in the middle of a shape, in the middle of a word. Nothing here needs you awake. Let's begin. Chapter 1. The word itself is a kind of confession. Geometry comes from two old Greek words. One of them means the earth, the ground under your feet. The other means measurement, earth measurement. Not perfect forms floating in some clean and weightless heaven. Just the measuring of dirt by people who needed to know where one field ended and the next one began. So begin there, in the mud, because that is honestly where it starts. Picture the Nile in late summer. Every year, the river swells with rain that fell far to the south, in mountains most Egyptians would never see, and it comes up over its banks and spreads across the valley floor. It carries silt with it, dark and fine and rich, and when the water finally pulls back, it leaves that silt behind as a gift. The soil is renewed, the crops will grow, but the water has also taken something. The boundary stones are gone. The little ridges and markers that said, this strip of land belongs to that family, have been smoothed away under a fresh layer of mud. Every farmer knows roughly where his field was. Roughly is not good enough when the harvest and the tax are both counted from it. So, each year after the flood, men walk out into the drying valley carrying rope. The Greeks later had a name for these men that translates as rope stretchers. The rope is knotted at regular intervals, and its trick is very simple and very deep. Take a length of cord, hold one end at a fixed peg, pull it taut, and you have made something the world does not otherwise hand you. You have made a straight line. Pull it taut and swing it around the peg instead, and you have made a circle. Almost all of the geometry that follows for the next several thousand years is contained in those two motions. A rope held tight and a rope swung around. They needed square corners too, and there are old suggestions that a loop of rope with knots at the right spacing could be pulled into a triangle with one perfect right angle in it. Whether the Egyptians actually did it that way is argued over, by people who study these things, and the honest answer is that we do not know for certain. What we do know is that the corners of their buildings are square to a degree that still surprises surveyors. You can let your eyes close for this part if they want to. The rope will still be there. What survives from Egypt is not theory. It is recipes. A long scroll, copied out by a scribe named Ames, something like 3,500 years ago, works through problem after practical problem. How much grain fits in this cylindrical granary? How to divide 9 loaves among 10 men? How to find the area of a field? There is a recipe in there for the area of a circle, and if you follow it, you get an answer that is less than 1% away from the truth. Nobody explains why it works. It works, and that was enough. And for 3,000 years, that was what mathematics meant. Further east, in the flat land between 2 other rivers, people were pressing wedge shapes into wet clay and doing something similar. The Babylonians counted in 60s, which sounds strange until you look at a clock, or at the 360 degrees we still cut a circle into. That is, their inheritance. Sitting quietly on your wrist, one of their tablets is famous. It is a broken rectangle of clay, about the size of a paperback, covered in 4 columns of numbers, and it was written well over 1,000 years before anyone had heard of Pythagoras of Samos. The numbers on it are the sides of right triangles, not small easy ones either. Some of the values are enormous, the kind you do not stumble on by accident while sketching, which means that somebody in Babylon, working with reeds and clay and no algebra at all, understood the relationship between the sides of a right triangle deeply enough to generate examples of it on purpose. What the tablet was for is still debated. A teaching aid, perhaps, a reference table for building, a piece of pure curiosity. Scholars disagree, and it is rather lovely that they do, because it means the tablet still has something to say. And yet, for all of this, something is missing from every one of these documents. Nobody asks, why? Nobody in those scrolls writes the sentence that would change everything, which is roughly this: I can see that this works for the fields I have measured. But does it have to work for every field? For every triangle that could ever exist, including the ones nobody will ever draw? That question arrives with the Greeks, and the first name attached to it is Thales of Miletus. He lived in a port city on the coast of what is now Turkey, around 2,500 years ago, and he seems to have been a merchant who traveled, which in that era meant Egypt and Babylon, and the accumulated knowledge sitting in both. The stories about him were written down centuries after he died, so hold them loosely. They are more like family stories than records. The best of them goes like this. Thales is standing at the base of a pyramid, and someone asks how tall it is. He does not climb it. He waits. He watches his own shadow on the sand until the moment when its length is exactly equal to his own height. Then he turns and measures the shadow of the pyramid and says, "That is how tall it is." He is right. And the reason he is right is that the sun's rays arrive at the same angle for him and for the pyramid. So the small triangle made of his body and his shadow has exactly the same shape as the huge triangle made of the pyramid and its shadow. Same shape, different size. What is true of one is true of the other, that idea. That shapes can be alike without being equal, and that the small one can therefore speak for the large one, is one of the most useful things anybody has ever noticed. It is how you measure a mountain you cannot climb, a river you cannot cross, a star you cannot visit. Thales is also credited with a handful of the first statements ever proved, rather than merely observed, that the two base angles of a triangle with two equal sides are equal to each other, that any triangle drawn inside a circle with its longest side on the diameter will have a right angle at the far corner every single time, no matter where you put that corner, whether he truly proved them or whether later Greeks simply gave him the credit because a founder is a convenient thing to have, we cannot say. But the shift is real, and it happened somewhere in that century. Measurement became reasoning. The rope became an argument. Let all of that settle now. The flood has gone down, the fields are drawn again, and the men with the rope have gone home for the evening. There is nothing left out there tonight but flat drying ground and the marks where the pegs went in. Chapter 2. Move forward a couple of centuries and about 1,000 miles to a young city on the Egyptian coast with a harbor, a lighthouse, and a library that is trying to collect every book in the world. This is Alexandria, roughly 300 years before the Common Era, and somewhere in it there is a teacher we call Euclid of Alexandria. We know almost nothing about him. Not where he was born, not what he looked like, not when he died. There is a quiet suggestion among some historians that Euclid may not have been one man at all, but a group of scholars working under a shared name, and while that is a minority view, it is a reminder of how little there is to hold. What we have instead is the book. It is called The Elements, and it is 13 books all long, and it did something no book had done before. It took nearly everything the Greek world knew about shape and put it in order, so that nothing appears until the things it depends on have already been established. Every result stands on results that came earlier. Nothing is borrowed from the future. That book stayed in classrooms for more than 2,000 years. Children in Victorian England learned from editions of it. Abraham Lincoln is said to have worked through parts of it by lamplight to teach himself what a real argument looks like. For a very long time, it was claimed that no book other than the Bible had been printed more often. And whether or not that claim survives close checking, the shape of it is right. Almost nothing written by human beings has been read continuously for that long. Here is how it opens, and the opening is the whole point. It begins with definitions. A point is that which has no part. A line is breadthless length. The ends of a line are points. A straight line is one that lies evenly with the points on itself. There is something almost tender about these sentences. He is trying to say what a point is, knowing that no point has ever been seen, because anything you can see has width. Then come what he calls common notions, which are the things too obvious to argue about. Things equal to the same thing are equal to each other. If you add equal things to equal things, the results are equal. The whole is greater than the part. And then 5 postulates. These are the requests. the things he asks you to grant him before he begins, because they cannot be proved from anything simpler, and something has to be granted, or nothing can ever start. The first is that you can draw a straight line from any point to any other point. The second is that you can extend a straight line as far as you like in either direction. The third is that given any center and any distance, you can draw a circle. The fourth is that all right angles are equal to each other. And the fifth is this: if a straight line crosses two other straight lines, and on one side, the two inside angles add up to less than two right angles, then those two lines, extended far enough, will eventually meet on that side. Read those 5 again in your mind, if you are still with me, and notice what has just happened. The first 4 are things you could say while pouring tea. The 5th is a paragraph. It has conditions in it. It asks you to imagine extending lines indefinitely into a distance no one can inspect, and to accept what happens out there. Euclid himself seems to have been uneasy about it. He avoids using it for as long as he possibly can, getting through 28 propositions before he finally reaches for it. It sits in his foundations like a stone of the wrong shape, and it is going to sit there, quietly, for 2,000 years, and almost everything in the rest of this night comes out of it. There is no need to hold on to that. It will still be uneven when you come back to it. For now, feel what it is like when the machine starts running. The very first proposition in the very first book asks you to build an equilateral triangle, a triangle with 3 equal sides, starting from nothing but a single line segment, and he does it like this. Put your compass point at one end, open it to the other end, and draw a circle. Now put your compass point at the other end, open it back to the first, and draw a second circle. The 2 circles cross. Draw lines from that crossing point down to both ends of your original segment. Every one of those 3 lines is a radius of one of the circles, so every one of them is the same length. So the triangle is equilateral. Done. There is no measuring anywhere in that, and no trial. The triangle did not come out equal by luck. It could not have come out any other way. That feeling is what the elements is really teaching, underneath the shapes, not facts about triangles. The experience of being convinced by something that has nothing to gain from convincing you. The book is not only geometry, either. Tucked into the 9th book is a proof that the prime numbers never run out, an argument so clean that mathematicians still teach it in the original form. Suppose you had a complete list of every prime. Multiply them all together, add 1, and whatever you now have is either a new prime or is divisible by a prime not on your list. Either way, the list was never complete. It cannot be completed. There is no largest one. There is a story about Euclid and the king, Ptolemy I, who was apparently finding the elements heavy going, and asked whether there might be some shorter path through it. Euclid is supposed to have answered that there is no royal road to geometry. Like most good lines from the ancient world, it was written down centuries later by someone who was not there, so enjoy it as a story rather than as a transcript. And there is the tradition that Plato of Athens had words carved above the entrance to his school, saying that no one ignorant of geometry should come in. That inscription is probably a later invention too, but it was invented because it felt true to the people who repeated it. Geometry was not a subject you took. It was the training that made you fit to think at all. The remarkable thing is how much of the elements is still correct. Not approximately correct, not correct for its time. Correct. If you draw those figures on a flat sheet of paper tonight, every single result holds, exactly as written, 23 centuries later. The trouble, when it eventually comes, is not that Euclid made a mistake. He did not. The trouble is that flat paper was never the only surface in the world, and one of his 5 requests quietly assumed that it was. Let the library go dark now. The scrolls are rolled and shelved. The lamp at the end of the long room has been put out, and every proof inside is going to be just as true in the morning, whether anyone reads it or not. Chapter 3. Step back a couple of centuries from that dark library, and south and west, across the water, to a Greek colony on the heel of Italy, where a man has founded something that is not quite a school and not quite a religion. His name is Pythagoras of Samos, and almost everything you have heard about him may be wrong. He wrote nothing down, or nothing that survived. His followers lived communally, kept their findings within the group, and had a habit of crediting discoveries back to the founder, whether or not he had made them. So the figure who reaches us is less a person than a fog with a name on it. What we can say is that a community existed, that it took mathematics seriously as a path to understanding the world, rather than as a tool for surveying fields, and that the idea at its center was that number is what reality is actually made of. They noticed, for instance, that music obeys arithmetic. Take a taut string and pluck it. Now stop it exactly halfway along and pluck again, and you get the same note, higher. The interval we call an octave. Stop it at 2/3 of its length, and you get a fifth. The interval that opens almost every anthem you have ever stood up for. Simple whole number ratios, and out of them comes something that makes people cry at weddings. If you had found that, you might also have concluded that the universe was built out of numbers. And then there is the theorem. Almost everyone carries some version of it, usually as a mumbled formula about squares on sides, and the formula hides how physical the thing actually is. So put the formula down for a moment and look at the picture instead. Threek a right-angled triangle, one corner square, the other two whatever they happen to be. Now, on each of its 3 sides, build an actual square, growing outward, like 3 rooms attached to the 3 walls of a triangular courtyard. The 2 smaller rooms sit on the 2 shorter sides. The big room sits on the long side, the one opposite the square corner. The claim is about floor space. If you could lift the floors out of the 2 small rooms and lay them into the big room, they would fill it exactly. Not nearly. Exactly. Every time, for every right triangle that has ever existed or could exist. That is a strange thing for the world to agree to. There is no obvious reason why area should behave like that, and yet you can see it. If you take a certain famous arrangement of 4 identical triangles inside a square and slide them around into a different arrangement inside the same square, what is left uncovered before the slide is the big room. What is left uncovered after the slide is the two small rooms, same square, same four triangles, so the same leftover space. The proof is a rearrangement of furniture. You are welcome to stop following the furniture at any point and simply drift. The rooms will still fit. The theorem was not his, by the way, and the honest history is more generous than the legend. Those Babylonian tablets already contain the relationship more than 1,000 years earlier. In India, the ritual texts on altar building, the ones associated with Baudhayana, state it plainly, because if you are building an altar of a precise area, you need to lay out right angles and diagonals correctly. In China, it appears as the Gogu rule, illustrated with a diagram and a slide the triangles argument of its own. Several civilizations found it separately, which tells you something. That relationship was already sitting in the structure of flat space, waiting for anyone who looked carefully enough at a rope and a corner. What the Greeks added was the demand that it be true for all cases and the willingness to prove it. It sits in Euclid's first book as the 47th proposition, and it is the hinge on which an enormous amount of what follows turns, because it is the first bridge between shape and number. Once you have it, distance becomes calculable. Once distance is calculable, the door opens to coordinates, to navigation, to physics. Every time your phone works out how far you are from somewhere else, that theorem is running underneath in a form that a scribe in Babylon would recognize. But it also broke something. Take the simplest right triangle you can imagine. Both short sides exactly 1 unit long, 1 handspan, 1 anything. What is the length of the diagonal? By the theorem, the square built on the diagonal must have an area of 2, so the diagonal is whatever number multiplies by itself to make 2. It clearly exists. You can draw it. It is sitting right there on your page. A definite length you could hold. A thread against. And for the Pythagoreans, who believe that everything in the world could be expressed as a ratio of whole numbers, this ought to have been a small task. Find the 2 whole numbers whose ratio gives that diagonal. Somebody at some point tried, and then tried harder, and then proved that it cannot be done. Follow it slowly, because it is one of the loveliest arguments ever made, and it fits in a paragraph. Suppose that length can be written as 1 whole number divided by another. Cancel everything that will cancel, so the fraction is in its simplest form, which means the 2 numbers are not both even. Now, square both sides. You find that the top number multiplied by itself equals twice the bottom number multiplied by itself. So the top number squared is even, which means the top number itself must be even, since odd numbers only ever square to odd. So write the top number as twice something. Substitute it back, tidy up, and out falls the fact that the bottom number squared is also even, so the bottom number is even too. But we began by saying they were not both even, so there is no such pair of whole numbers. There never was. The diagonal of a perfectly ordinary square, a shape a child can draw, has a length that cannot be captured as any ratio of whole numbers at all. There is a story that the man who let this out of the group, sometimes named as Hippasus of Metapontum, was drowned at sea for it, either by the gods or by his colleagues. Treat that as a legend. It surfaces in sources written many centuries afterwards. The details shift from telling to telling, and there is no good reason to believe it happened. What is probably true is that the discovery was uncomfortable because it dismantled the belief the whole community was resting on. And here is the gentle part. Nothing bad happened. The world did not become less orderly. It turned out that whole numbers and their ratios, which had seemed to be all the numbers there were, are only a thin scattering among the numbers that actually exist. Between any two of them sit infinitely many lengths that no ratio will ever name. Those lengths were always there, in every square anyone had ever drawn, patiently unnamed. Mathematics did not shrink that night. It got quietly, permanently larger. So let it be larger. The square is still on the page where you drew it, and the diagonal still runs corner to corner, exactly as long as it always was, needing no name from anyone in order to lie there. Chapter 4. Now the Greek world does something that still seems slightly unreasonable. Armed with nothing but shapes, shadows, and stubbornness, it goes out and measures things nobody has ever stood next to. Begin with a circle, and with the oldest question you can ask about one. Walk around the rim of a circular pond, and you cover a certain distance. Walk straight across it, and you cover a shorter one. Divide the first by the second, and you get a number. And here is the quiet miracle. That number is the same for every circle in the universe. A wedding ring, a dinner plate, the orbit of a moon. Draw any circle at all, measure round and measure across, divide and out comes the same value. We call it pi. The trouble is that it is not a comfortable value. It is a little more than 3, and the little more never resolves into anything tidy. Archimedes of Syracuse decided to trap it. He lived in Sicily in the 3rd century before the Common Era, and his method has the elegance of a snare. Draw a circle. Inside it, draw a regular hexagon whose corners touch the rim. The hexagon's perimeter is obviously shorter than the circle, since it cuts corners. Now draw a hexagon outside the circle, just touching it. That perimeter is obviously longer. You have caught the circle between two numbers you can actually calculate. Then he doubles the number of sides and doubles it again, from 12 to 24 to 48 to 96. Each time, the inner shape hugs the circle a little more tightly, and the outer shape settles a little closer, and the gap between the two numbers narrows around the truth like a hand closing. At 96 sides, he stopped and reported his result. Pi lies between 3 and 10/71 and 3 and 1/7. He was right. Both bounds hold, and he did it without decimal notation, without algebra, without any of the symbolic machinery that makes such work tolerable, extracting square roots by hand in a number system that was not designed for it. If you have ever wondered what genius actually looks like from the outside, it looks like someone doing an enormous amount of arithmetic for a reason nobody asked them to care about. He also found something he seems to have loved more. Take a sphere. Now imagine the smallest cylinder that will just contain it, snug at the sides, touching top and bottom. Archimedes proved that the sphere's volume is exactly 2/3 of that cylinder's, and that its curved surface is exactly 2/3 as well. A ball and the tin it came in, related by a simple fraction. He asked for that figure to be carved on his tombstone. The sphere inside the cylinder, with the ratio written beside it. And roughly a century and a half after his death, a Roman official named Marcus Tullius Cicero, serving in Sicily, wrote that he went looking for the grave, found it overgrown with brambles outside a city gate, and recognized it by the shape cut into the stone. Let your breathing slow here if it wants to. There is nothing urgent in any of this. There is a stranger postscript, one of Archimedes' works, in which he explains how he actually found his results before proving them, survived only because a medieval scribe scraped the ink off the parchment and wrote a prayer book on top of it. The faint traces underneath were recognized in 1906 by a Danish scholar named Johann Ludwig Heiberg, and then read properly a century later with modern imaging. A book that came within a knife blade of being lost forever, hiding under Psalms for 800 years. While Archimedes was in Sicily, a friend of his was running the library at Alexandria and had a question about the size of the planet. Eratosthenes of Cyrene had heard that in the southern town of Syene, on one particular day of the year at noon, the sun shone straight down to the bottom of a deep well and cast no shadow at all directly overhead. Meanwhile, in Alexandria to the north, on that same day, at that same hour, a vertical pole did cast a shadow. If the earth were flat, that could not happen. Sunlight arrives in effectively parallel rays, so a flat world would give every pole the same shadow at the same moment. A shadow here and no shadow there means the ground itself has tilted between the two places. The world is curved, so he measured the angle of that shadow and found it to be about 1/50th of a full turn, which means the distance from Alexandria to Syene is about 1/50th of the way around the entire planet. Find that distance, multiply by 50, and you have the circumference of the world. He got a number. How good it was, we honestly cannot say, because he reported it in units called stadia, and we are not certain how long his stadion was. Depending on which value you use, his answer is either startlingly close to the modern figure or merely respectable. Popular retellings often quote the flattering version, as though it were settled. The uncertainty is real, and it does not diminish him in the slightest. A man with a stick, a well, and a walking distance worked out the size of the earth, and the method is exactly right even where the units are foggy. One more from this era, because it becomes important much later. Apollonius of Perga studied what happens when you slice a cone. Cut it straight across, and the edge of the cut is a circle. Tilt your knife a little, and you get an ellipse, a stretched circle. Tilt it until the cut runs parallel to the cone's own slope, and the curve stops closing and runs away forever, and that one is a parabola. Tilt further still, through both halves of a doubled cone, and you get the two open branches of a hyperbola. Narrow, ellipse, parabola, hyperbola. He gave them those names. He filled 8 books with their properties, and there was no use for any of it. It was pure play, done for the pleasure of the structure. 18 centuries later, those 4 curves turn out to be the shapes of planetary orbits, the path of a thrown stone, the cross-section of a headlight, the surface of a satellite dish, and the route of a spacecraft slingshotting past a moon. Nobody in Perga could have known. That happens more often in this story than you might expect. The keeping of all this was work in itself, and one of the people who did it was Hypatia of Alexandria, a mathematician and astronomer, who taught in that city around the turn of the 5th century. She wrote commentaries on Apollonius and on the astronomy of her day, and commentary in that world meant something closer to editing and explaining, the labor that keeps difficult books usable for the next generation. She was killed in the political violence of her city in 415, and much of her own writing is lost. What survives of the Greek tradition survives partly because people like her spent their lives copying, correcting, and explaining it. So let all of those measurements rest where they are. The pond, the ball in its tin, the well with the sun at the bottom of it, the cone quietly waiting for someone to need it. None of that has anywhere else to be tonight, and neither do you. Chapter 5. We have to go back now to the stone of the wrong shape, the 5th of Euclid's 5 requests, because for the next 2,000 years, it is going to be the most quietly troublesome sentence in mathematics. There is a friendlier way to say it, and it is the version taught in schools now. A Scottish mathematician named John Playfair put it in this form in 1795, though the idea was floating around long before him. Take a straight line. Take a point that is not on it. Now, through that point, how many lines can you draw that run alongside the first one forever without ever meeting it? The answer feels obvious, and the obvious answer is exactly 1. Tilt your line the tiniest fraction either way, and far enough out, it will eventually cross. There is precisely one perfect setting, and that is the parallel. That statement is equivalent to Euclid's 5th postulate. Grant one, and you get the other, and every consequence you were ever taught about triangles depends on it. The angles of a triangle adding to 180 degrees, that comes from this. The theorem about squares on the sides of a right triangle comes from this. Rectangles existing at all comes from the. Pull this one sentence out and an astonishing amount of school mathematics comes out with it. So here is the thing that gnawed at people. Look again at Euclid's first 4 requests. You can join 2 points. You can extend a line. You can draw a circle. All right angles are the same. Each of those is a single breath, and each is about something you could check in front of you on a table. The 5th asks you to know what 2 lines do after they leave the room. It does not feel like a request. It feels like a fact, and facts are supposed to be provable. Surely, people thought, this one is a theorem in disguise. Surely someone can derive it from the other 4, and then the foundations will be clean. That project ran for 20 centuries, and it never once succeeded. And the story of the failures is one of the most moving things in the history of thought. Proclus of Athens, writing his commentary on Euclid in the 5th century, records that people were already attacking the problem in antiquity, and offers an attempted proof of his own. It does not work. Somewhere in it, he has quietly assumed something equivalent to the very thing he is trying to prove, which turns out to be the trap that catches almost everybody. The work moved east. In Cairo, Hassan ibn al-Haytham better known for his studies of light and vision, tried an approach using a moving line, and the figure it sweeps out. In Persia, a poet you may know for entirely different reasons, Omar Khayyam, whose verses about wine and impermanence are still in print, spent serious effort on a quadrilateral with two equal sides standing perpendicular to a base. He asked what the two top angles must be. If they are right angles, you are in Euclid's world. If they are blunt, or if they are sharp, you are somewhere else. He explored those somewhere else's carefully, and then rejected them, on grounds he could not really defend. Nasser al-Din al-Tusi, working in the 13th century, went further with the same figure, and his treatment eventually reached Europe in a printed edition in Rome in 1594, where it was read by the English mathematician John Wallis, who took up the problem in turn. Ideas traveling from Alexandria to Baghdad to Persia to Rome to Oxford, hand to hand over more than 1,000 years, all circling the same short paragraph. You can let this drift past you like weather. It is not a puzzle you have to help with. Then, in 1733, a Jesuit priest in Milan named Giovanni Girolamo Saccheri published a book with a wonderfully confident title, promising that Euclid had been cleared of every flaw. His plan was the strongest one available. If you want to prove a statement, assume the opposite and show that it leads to nonsense. So, Saccheri took the same quadrilateral and assumed the top angles were sharp rather than right, meaning that through a point you could draw more than one parallel. Then he started deducing consequences, hunting for a contradiction. He found no contradiction. He found a world, triangles whose angles add up to less than 180 degrees, triangles whose angle shortfall grows as the triangle gets bigger, no rectangles anywhere. Similar figures that cannot exist at different sizes, so that knowing a triangle's angles fixes its size completely. Result after result, all of them strange, none of them contradicting each other. He was walking through an entirely coherent country and writing down its laws. And then, at the end, he declared that these results were repugnant to the nature of the straight line, and concluded that he had proved Euclid after all. He had not. He had discovered non-Euclidean geometry. Roughly a century before it was accepted, wrote it down accurately, and then apologized for it. He died a few months after the book appeared, believing he had defended the old world rather than found a new one. It is hard not to feel enormous fondness for him. He was looking for a contradiction so intently that he walked straight through a doorway without noticing. It was a doorway. Johann Heinrich Lambert, a generation later, came closer still. He worked through the same sharp angle case and noticed something remarkable, which is that in such a geometry, the area of a triangle is determined entirely by how far short its angles fall of 180 degrees. Bigger triangle, bigger shortfall, and there is a largest possible triangle you can never exceed. He also observed that the whole system behaved rather like the geometry on a sphere, but with a radius that was an imaginary number. He wrote that down. And then he too stepped back from the edge. Adrien-Marie Legendre, whose textbooks taught geometry to much of Europe, returned to the parallel problem over and over across roughly 40 years, publishing attempted proof after attempted proof through successive editions. Each one eventually found to contain a hidden assumption. 40 years of a distinguished career spent walking into the same soft ground. Look at the shape of all that effort. Century after century, in Alexandria and Cairo and Nishapur and Milan and Paris, people of real ability convinced themselves that a sentence about parallel lines simply had to be provable, and every single one of them either failed openly or smuggled in the assumption without noticing. Nem. They were not being stupid. They were being human. The statement sits so close to what a lifetime of living in a room full of straight edges makes you expect that doubting it was almost physically difficult. What none of them could quite let themselves think was the possibility that the postulate is not provable because it is not necessary, that you could refuse it, keep everything else, and end up somewhere just as consistent as where you started, somewhere real. Two men in the early 1800s are going to think exactly that, independently, 1,000 miles apart, and neither of them will get much thanks for it in his lifetime. But that can wait until you are further into the night. For now, let the sentence sit there as it has sat for 20 centuries, unproved, patient, entirely unbothered, in a book on a shelf, in the dark, chapter 6. While that sentence sat unproved on its shelf, geometry slipped out of mathematics altogether and went to work in the workshops of painters and came back changed. If you have ever looked at a medieval painting and felt that something was gently wrong with it, this is why. Space in those pictures is not organized by distance. It is organized by importance. The saint is large because the saint matters. The donor kneeling in the corner is small because he is paying, not starring. Buildings behind are stacked above rather than shrunk. It is a beautiful convention, and it is a convention, and everyone using it knew perfectly well that a distant man looks smaller than a near one. They simply were not painting what the eye receives. Then, in Florence, around 1413, an architect does an experiment on a public square. Filippo Brunelleschi was the man who would go on to raise the dome over the Florence Cathedral, a dome so large that nobody was entirely sure how it could be built until he built it. Before that, he made a small painted panel of the octagonal baptistery standing across the piazza, and he made it according to a rule he had worked out about how the receding edges of a building should behave. Then he did something theatrical. He drilled a small hole through the panel, right at the point where the viewer's eye belonged. You were to stand where he had stood. Hold the panel with its painted face away from you. Put your eye to the hole from behind, and hold a mirror out at arm's length so that the painting appeared in it. And then, at the right moment, you drop the mirror. The painting swings away, and the real baptistery is standing there behind it, in the same place, at the same size, with its edges running away at the same angles. The picture and the world lined up. He had not made something that looked pleasant. He had made something that looked correct, and he proved it by putting the two side by side. The rule underneath is one you already know with your body, even if you have never named it. Stand in the middle of a long straight road at night, or a corridor, or a railway line. The two edges are parallel. You know they are parallel. They never come nearer to each other in reality. And yet, as they travel away from you, they close steadily until they meet at a single point out on the horizon. Parallel lines meet, not in fact, but in appearance, and appearance is all a painting has. That meeting place is called the vanishing point, and once you have it, an entire construction follows. Leon Battista Alberti wrote the method down in a treatise on painting in 1435 and gave it the image that has stuck ever since, which is that the surface of a picture should be treated as an open window through which you see the scene. He explained how to lay out a tiled floor in perspective so that the rows recede correctly, which sounds like a small thing and is actually the key that unlocks the whole room. Piero della Francesca, who was both a serious painter and a serious mathematician, wrote his own treatise on the subject, and his paintings have a stillness to them that comes partly from how carefully the space is built. In Germany, Albrecht Dürer traveled to Italy specifically to learn this new craft, and afterwards produced woodcuts showing the machines that made it mechanical. A frame with a grid of threads, a taut string running from a point on the object to a fixed hook that stands in for the eye. Two men working patiently, plotting a lute one point at a time. None of that requires anything from you tonight. If sleep is arriving, go with it and let the drawing take as long as it likes without you. Then a French engineer takes the painter's trick and asks a mathematician's question about it. Gérard Desargues worked in Lyon and in Paris in the 1600s on fortifications, waterworks, and staircases, and in 1639 he published a short and extremely strange book, where the painters said that parallel lines appear to meet at the horizon. Desargues simply said that they meet. He added to the ordinary plane a set of new points, one for each direction, sitting infinitely far away, and he declared that parallel lines genuinely pass through the same one of these. That sounds like cheating. It is not. And the reason is that the resulting system is completely consistent and vastly tidier than what came before. Every 2 points determine a line, and now every 2 lines determine a point, with no exceptions and no special cases for parallels. The awkward gap in the middle of Euclid's world is filled in by simply admitting the horizon as part of the map. His most famous result is a small piece of quiet magic. Take 2 triangles positioned so that lines through their corresponding corners all pass through one common point, as if a lamp at that point were casting one triangle onto the other. Now extend the corresponding sides until they cross. Those 3 crossing points always lie on one straight line. Always. And you can see why the moment you allow yourself to think of the flat figure as a squashed picture of 2 triangles floating in space, cut by 2 planes. Desargues wrote in a private vocabulary borrowed from botany, calling things trunks and stumps and knots, and almost nobody read him. His book effectively vanished. What saved it was that a young admirer had made a handwritten copy, and that copy sat unnoticed until a mathematician named Michel Chazels came across it in a Paris shop. In 1845, more than 200 years later, One person did read Desargues at the time, and he was 16 years old. Blaise Pascal took the idea and proved that if you draw any 6 points on a conic section and join them in a closed loop, the 3 pairs of opposite sides meet in 3 points that lie on a single straight line. He was a teenager. His father's friends did not entirely believe he had done it. What this whole line of work uncovered is a different kind of geometry. One where distance and angle are not the important things, because a projection distorts both. A circle on the floor becomes an ellipse on the canvas. A square becomes a lopsided quadrilateral. Lengths change, angles change, and yet certain things survive every projection untouched. Straight lines stay straight. Points that lie on a line still lie on a line. Which points sit on which lines is preserved, and out of that skeleton, an entire geometry can be built. That idea of studying what survives when everything else is allowed to change will come back later tonight as one of the deepest thoughts in the whole subject, and the practical end of it is closer to you than you might think. Every 3-dimensional image you have ever seen on a screen, in a film, in a game, in an architect's walkthrough, is produced by taking points in a modeled space and projecting them onto a flat rectangle through a mathematical eye. The machine is doing Brunelleschi's experiment 60 times a second, and it is using the coordinates that Desargues would have recognized. Let the studio go quiet now. The panel with the little hole in it is propped against the wall. The mirror is put away, and the light across the empty piazza is doing what it has always done, whether or not anyone is painting it. Chapter 7. There is a piece of this that had to arrive from somewhere else entirely before the next step was possible, and it arrived from Baghdad. In the 9th century, a scholar named Muhammad ibn Musa al-Khwarizmi wrote a book about restoring and balancing quantities in equations. The Arabic word for the restoring part is al-jabr, and when the book made its way into Latin, that word came with it and became algebra. His own name, worn down through the same journey, became the word algorithm. 2 of the load-bearing words of the modern world, both belonging to one man who was working out how to divide estates fairly and calculate inheritances. For centuries afterwards, geometry and algebra sat in separate rooms. Geometry was pictures, and it was respectable because the Greeks had done it. Algebra was symbols and procedures, and it was regarded as the more mechanical trade. You could be excellent at one and indifferent to the other. Then, in 1637, a French philosopher published a book about how to think clearly and stuck 3 appendices on the back of it as demonstrations of his method. The book is the Discourse on Method. The philosopher is René Descartes, and the 3rd appendix quietly knocks down the wall between the 2 rooms. There is a story that the idea came to him while he lay in bed, as he apparently often did until late morning, watching a fly walk across the ceiling and realizing that he could specify exactly where the fly was at any moment with 2 numbers, its distance from one wall and its distance from another. It is a wonderful story, and there is no good evidence for it. Enjoy it anyway, and hold it loosely, the way we held the shadow of the pyramid. The idea itself is simple enough to see with your eyes closed. draw a horizontal line across the page and a vertical line down it, crossing somewhere in the middle. Now, every point anywhere on that page has an address, a pair of numbers, saying how far across and how far up it is. 2 numbers, 1 point. Nothing lost, nothing ambiguous. And now watch what happens to shapes. A circle is the set of all points at a fixed distance from a center. But we already know, from that theorem about squares on sides, how to write distance using coordinates. So a circle turns into a statement about numbers, a relationship that the pair of coordinates must satisfy, and every point that satisfies it lies on the circle, and every point that does not, does not. A straight line becomes a relationship where the 2 numbers rise together at a fixed rate. A parabola becomes what you get when one of them is squared. Those 4 curves that Apollonius of Perga carved out of his cone, purely for pleasure, all turn out to be the simplest possible relationships you can write down once you allow squares. Circle, ellipse, parabola, hyperbola, all of them second degree, all of them siblings, which was invisible when they were only slices of a solid, not shaft, had become sentence. Sentence had become shape, and the traffic runs both ways, which is the part that matters. If you have a shape and it is hard to reason about, you can convert it into an equation and grind through the algebra, which is tedious but reliable and never requires inspiration. And if you have an equation and it is opaque, you can plot it and look at it and suddenly see with your eye what the symbols were hiding. Anyone who has ever been rescued by drawing a graph knows what that feels like. A quiet note about credit. Pierre de Fermat, a lawyer in Toulouse who did mathematics in the evenings, had worked out essentially the same idea, and there is good reason to think he had it slightly earlier. He simply did not publish, as he mostly did not publish anything, preferring to write to friends and leave remarks in the margins of his books. So the coordinates carry Descartes' name, and Fermat's contribution is a footnote, which is roughly what happens to people who do not send things to the printer. What this unlocked is difficult to overstate without reaching for the kind of language we are avoiding tonight. So let us just look at what followed. Within 50 years, Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany had built calculus, and calculus is what you get when you ask coordinate questions about curves. How steep is this curve at this exact point? What area lies underneath it? Those are questions you can barely phrase with a compass and a straight edge, and they become answerable once a curve is an equation. Motion, orbits, falling bodies, the flow of heat, the shape of a hanging chain, all of it opens up. And there is one more consequence, which is the strangest and which becomes the doorway to everything. In the second half of this night, if a point on a page needs 2 numbers and a point in a room needs 3, one for across, one for along, one for up, then what is a thing that needs 4? Geometry, as pictures, cannot answer that. You cannot draw it. But geometry as arithmetic does not care in the slightest. A list of 4 numbers is a perfectly well-behaved object. You can measure the distance between 2 such lists using exactly the same rule, extended by one more term. You can ask about spheres in that space, and rotations, and shortest paths, and everything works, and nothing anywhere complains that you have run out of directions. That is the moment when geometry stops being about the space we live in and becomes about any space you can consistently describe. The pictures do not follow you there. The reasoning does. You do not have to picture the fourth direction. Nobody can. Let that go, and let your body go heavier into the mattress while you are at it. There is one more thing worth saying about coordinates before we leave them, because it is sitting in the room with you right now. Every screen you own is a grid of points with addresses. When something moves across it, a machine is recalculating pairs of numbers. When a photograph is rotated, a matrix is turning coordinates into other coordinates. When a map application draws your route, it is holding your position as a pair of angles on a curved surface and projecting them onto a flat rectangle in your hand, which is a problem we are going to see is not entirely solvable in the very next stretch of the night. All of that is Descartes' appendix, running quietly, several billion times a second, around the world, in devices he could not have imagined, doing exactly the thing he described. So, let the grid rest. The horizontal line, the vertical line, and all those points sitting patiently at their addresses, none of them going anywhere, all of them still exactly where you left them. Chapter 8. Now we come to the orange peel, and to the man who explained why it tears. Carl Friedrich Gauss was born in Brunswick in 1777 to a family with no money and no books. There is a well-worn story that as a small boy, he was set the task of adding all the whole numbers from 1 up to 100 as a way of keeping the class quiet, and that he produced the answer almost immediately by noticing that the numbers pair up from the outside in, each pair adding to the same total. Like most childhood stories about famous people, it has been polished over the years, but something in that direction seems to have happened, because his teachers noticed him early enough to find him a patron. At 19, he made a discovery that decided his life. Since the Greeks, it had been known how to construct certain regular polygons using only a compass and an unmarked straight edge. 3 sides, 4, 5, 6, 15. Nobody in 2,000 years had added to the list. Gauss proved that a regular polygon with 17 equal sides could be constructed. And more than that, he worked out exactly which regular polygons are constructible and which are forever impossible. He was so pleased with the 17-sided figure that he asked for it on his gravestone, the way Archimedes of Syracuse had asked for his sphere and cylinder. But the work that matters most for tonight came from a job, and the job was surveying. From 1818 onwards, Gauss spent years running the geodetic survey of the Kingdom of Hanover. That meant standing on hilltops in the rain, sighting between distant points, and building up a web of triangles across the countryside, measuring angles to a precision that his instruments could barely deliver. He invented a device for it, a heliotrope, which used mirrors to flash sunlight from one station to another, so that a surveyor 30 miles away had something bright and exact to aim at. Years of that. Triangles laid over hills and valleys, on ground that was not flat and was never going to be flat. And somewhere in the middle of all that tedious field work, He arrived at the idea that changes everything. Here is the idea, and it is worth going slowly. Take a sheet of paper and roll it into a tube. Have you bent it? Obviously. It is curved now. You can feel the curve under your fingers. But notice what did not happen. Nothing stretched. No part of the paper had to grow or shrink. Every distance measured along the surface of the paper is exactly what it was before. If you had drawn a triangle on the flat sheet, its sides are the same lengths on the tube, and its angles still add to 180 degrees. Now try the same thing with a sphere. Try to wrap a flat sheet of paper smoothly around a ball, with no folds, no creases, no cuts. You cannot. It will not go. Something has to be forced. So, there are two different meanings of curved, and Gauss separated them cleanly. The first is about how a surface sits in the surrounding space, and it is the one your hand feels. A rolled tube is curved in that sense. The second is deeper. It is about whether the surface itself, considered on its own terms, is stretched. And the astonishing part is that this second kind of curvature can be detected by someone living inside the surface, who has no idea that any surrounding space exists at all. Imagine an ant, a very flat, very patient ant, living entirely within a surface, with no concept of up or off. It cannot step back and look. All it can do is crawl and measure. That ant can still work out the shape of its world. It walks in a straight line for a certain distance, plants a pin, and then walks a circle around that pin, always keeping the same distance from it, and measures how far it walked to get all the way round. On a flat surface, the answer comes out as pi times twice the radius, exactly as expected. On the surface of a sphere, the answer comes out too small. The circle closes sooner than it ought to, because the surface is quietly gathering itself in. On a saddle-shaped surface, the answer comes out too large, because there is extra material ruffled in around the pin. Or the ant draws a triangle and adds its angles, more than 180, and the world curves like a ball, less, and it curves like a saddle, exactly 180, and it is flat. The ant never leaves its surface, and never sees it from outside, and still the ant knows. If your attention has been wandering, that is the one thing worth keeping, and you are free to keep it while you are already half asleep. Gauss published this in 1827, and he was so struck by it that he gave the result a name meaning the remarkable theorem, which is an unusually excitable thing for a man of his temperament to do. The content of it is that this intrinsic curvature does not change when you bend a surface without stretching it. It belongs to the surface itself, not to how the surface is posed in space. And that is why the orange peel tears. The peel has the intrinsic curvature of a sphere. The table has the intrinsic curvature of a plane. Those two numbers are different, and no amount of gentle bending will convert one into the other, because bending does not touch that quantity. To flatten the peel, you must stretch it or tear it. The tearing is not clumsiness. It is arithmetic, which means, and this follows immediately, that there is no honest flat map of the earth. Not a difficult one, not one waiting for a cleverer cartographer. There cannot be one, ever. For the same reason, there is no largest prime. Every map you have ever used is therefore a compromise, and every mapmaker has to choose what to sacrifice. The familiar C-chart projection keeps angles correct, which is exactly what you want when you are steering a ship by compass and pays for it by inflating everything far from the equator, which is why Greenland looks like a rival to Africa on a classroom wall when it is in truth a fraction of the size. Other projections keep areas honest and let the shapes go strange. You can have angles or you can have areas. The surface will not let you have both. There is a small version of this you can do at dinner. Take a floppy slice of pizza and it droops over your hand. Fold it gently along the middle into a shallow trough and suddenly it holds itself out straight. Nothing was added. What happened is that the slice must keep its intrinsic curvature at 0. So once you force it to curve one way across the middle, it is forbidden from curving the other way along its length. Corrugated iron roofing is rigid for exactly the same reason. There is a persistent story that Gauss used his survey and a great triangle between 3 German mountains to test whether physical space itself is curved. Historians have gone back and forth over this, and the balance of opinion now is that the measurements were made for ordinary map-making purposes, and that the tale grew in the retelling. What is certain from his letters and unpublished notes is that he had been thinking privately about geometries where Euclid's 5th request fails, that he believed such geometries were consistent, and that he chose not to publish, saying in one letter that he feared the outcry of the dull. He was probably right that there would have been an outcry, and because he stayed quiet, the announcement was left to other people in other countries who had no idea he had been there before them. But that is for a little further on. For now, just rest with the ant. It is still out there on its curved little world, measuring circles that come out slightly too small, entirely content, in no hurry at all. Chapter 9. So it fell to 2 men who had never met and who never would meet, working about 1,000 miles apart on the same impossible idea at almost the same time. The first is Nikolai Ivanovich Lobachevsky, who spent essentially his whole life at the university in Kazan on the Volga, far out on the eastern edge of European Russia. He taught there, he became its rector, he ran its library and its observatory, and in 1829 he published a paper in the local university journal, in Russian, setting out a geometry in which the parallel postulate is simply false. He did not present it as an error to be corrected. He presented it as a country to be described. Through a point not on a given line, he said, "Let there be not one parallel, but infinitely many, a whole fan of lines that never meet the original." Then he worked out, carefully and at length, what such a world is like. The reception was cold. The paper was in Russian, in a provincial journal, and when it did get noticed, the notice was hostile. He kept going anyway, for decades, publishing revised versions, in French and in German, going blind toward the end, and dictating a final account of the whole thing in the last year of his life. He died without knowing that he had been right. The second is János Bolyai, a Hungarian army officer, an excellent violinist, and, by report, a formidable swordsman. His father, Farkas Bolyai, was a mathematician who had spent years of his own life on the parallel postulate, and who had known Gauss as a student. When Janos wrote to say that he was working on it, his father wrote back with something close to grief, begging him to leave it alone, saying that he himself had passed through that bottomless night, and that it had swallowed all the light and joy out of his life. "Give it up," he wrote. "Fear it no less than the passions of the senses." Janos did not give it up. In 1823, he wrote to his father that out of nothing he had created a strange new universe. His account of it appeared in 1832 as an appendix at the back of one of his father's textbooks, about 24 pages long, and those 24 pages are a complete and beautiful foundation for a geometry nobody had accepted was possible. Fractals proudly sent it to Gauss. Gauss wrote back that he could not praise the work, because to praise it would be to praise himself, since he had reached the same conclusions 30 or 35 years earlier, and had simply not published. He added that he was glad it was the son of his old friend who had got there. He may well have meant that kindly. It landed on Janos like a stone. He suspected his ideas had been taken. He grew bitter. And when he later learned that a Russian had published something similar, 3 years before his own appendix, he came close to breaking. He published almost nothing else for the rest of his life. 2 men, then, and neither of them was thanked. That is the human cost of the discovery, and it is worth sitting with for a moment before we look at what they actually found, which is lovely. Let your shoulders drop. None of this needs holding. In their geometry, sometimes called hyperbolic, the world behaves like this. Triangles have angles that add up to less than 180 degrees, and the bigger the triangle, the further short the total falls. There is a largest possible area a triangle can have, no matter how far you extend its sides. Rectangles do not exist because you cannot have 4 right angles in a closed 4-sided figure, and there are no similar figures at different sizes, which means that shape and size are locked together. In such a world, if you describe a triangle's angles over the telephone, you have described its size exactly. There is a natural unit of length built into space itself. For a long time, nobody could be sure the whole thing was consistent until the models arrived. Eugenio Beltrami showed in 1868 that you could build a piece of this geometry inside ordinary Euclidean space on a trumpet-shaped surface, which meant that if hyperbolic geometry contained a contradiction, then so did Euclid's, and hardly anyone was willing to say that. Then, Henri Poincaré gave a picture you can actually look at, and it is one of the most charming objects in mathematics. Take a flat disk. Declare that the boundary circle is infinitely far away, and that measured distances swell enormously as you approach it, so that a creature walking toward the edge takes smaller and smaller apparent steps and never arrives. Straight lines in this world appear to us as arcs of circles that meet the boundary at right angles. Everything looks bunched and shrunken near the rim, and to the inhabitants everything is perfectly uniform because their rulers shrink along with them. If that sounds familiar, it may be because the artist Moritz Cornelis Escher built several prints on exactly this model, filling a circle with angels and devils and fish that grow smaller and smaller toward the edge in an infinite regress. He worked from a diagram in a paper he barely understood and produced a picture of a whole infinite world sitting inside a circle you could cover with your hand. You can also hold one thanks to a mathematician named Dinah Taimina, who realized in the 1990s that a hyperbolic surface can be crocheted. You simply increase stitches at a steady rate, and the fabric has no choice but to ruffle more and more into a floppy coral-like frill. Suddenly, the geometry that took 2,000 years to permit is a soft thing in a basket, and students can push their fingers along its straight lines. Nature had been making them the whole time. Kale leaves and lettuce edges ruffle for this reason. So do certain corals and the flanges of some sea slugs. The frill is what a surface does when it has more area than a flat sheet knows what to do with. And there is a third possibility, which is easier still, because you have been standing on it your whole life. On the surface of a sphere, straight lines are great circles, the largest circles you can draw, like the equator or any line of longitude. Any two of them cross twice, which means there are no parallels at all. Triangles have angles adding to more than 180 degrees, as in that walk from the North Pole to the equator and back. Navigators had been doing this geometry for centuries without ever calling it a rival to Euclid, so the picture resolves. Euclid was not wrong. He was describing one of at least three consistent possibilities, the flat one, and it looked like the only one, because we are small and the ground is large and the room is square. The question that opens up next is the interesting one. If there are several possible geometries, which one is our own? That question is going to take another 80 years to answer, and the answer is going to be stranger than anyone expected. For tonight, though, just let the crocheted frill sit in its basket, ruffling gently at the edges, being an entire infinite plane, while taking up almost no space at all. Chapter 10. There is a particular afternoon in June 1854, in a lecture room at the University of Göttingen, that is probably the single most consequential hour geometry has ever had. Almost nobody present understood what they were hearing. The speaker is Bernhard Riemann. He is 27, the son of a country pastor, painfully shy, in poor health, and very poor in the ordinary sense as well. To qualify for the right to lecture, he has to give a trial lecture to the faculty, and the custom is that the candidate submits 3 possible topics and is assigned the first one, which is why every candidate puts real effort into the first and rather less into the third. Riemann's third topic was the foundations of geometry. Gauss, who was on the committee and was by then an old man with less than a year to live, ignored the custom and chose it. So Riemann had about 7 weeks to build, from very little, a lecture on what geometry actually is. And because his audience was the whole philosophical faculty, including people who had never followed a calculation in their lives, he had to do it almost entirely in words. What he gave them starts by taking everything apart. Forget shapes, he says in effect. Forget lines and circles and the plane. Start with something much barer. Consider a collection of things, any things, where each one is specified by a certain number of measurements. Positions on a surface need 2. Positions in a room need 3. The states of a gas might need many. He calls such a collection a manifold, and the word is meant to be as unglamorous as it sounds. It is just a smooth set of possibilities with a certain number of independent directions of variation. Then he adds one thing, and only one thing, and out of it the entire subject falls. He adds a rule for measuring distance between neighboring points. That is all. Not a rule for the whole space, just a local rule, a statement of how far apart 2 points are when they are extremely close together. Give me that rule, Riemann says, and I will give you back the geometry. Because if you know local distances everywhere, you can find the length of any path by adding up along it, and once you can measure paths, you can ask which path between 2 points is shortest, and those shortest paths are what deserve to be called the straight lines of this world. Angles follow, areas follow, curvature follows, and it can be different in different places. More curved here, flatter there, varying smoothly from region to region like temperature. The flat geometry of Euclid is one choice of the local rule. The sphere is another. The hyperbolic world of Lobachevsky and Bolyai is a third, and those 3 are barely the beginning of what the rule permits. Also, of course, none of this cares how many numbers you needed in the first place. 2, 3, 4, 11. The reasoning does not change. Riemann simply proceeded in as many dimensions as anyone might want, without apology, without pictures, and without anything going wrong. You do not have to keep up with any of that. It is enough to know that somebody widened the room. Let yourself sink a little deeper while I finish the story, because the last part of the lecture is the part that matters most, and it is the part that would have sounded to that audience like a young man overreaching. Riemann pointed out that geometry, understood this way, is no longer something you can settle by pure thought. If space is a manifold with a local rule of distance, then which rule it actually has is a question about the physical world, and physical questions are answered by measurement. He suggested that the geometry of space in the very small might not match the geometry we see at ordinary scales, and that the same might be true in the very large. And he ended by saying that this leads out of mathematics and into the domain of physics, and that he could go no further. Then he stepped down. Gauss, who by every account was not an easy man to impress, and who had spent much of his own life circling these questions in private, is reported to have left the room in a state of unusual excitement, and to have spoken warmly of the lecture on the walk back, which for Gauss was a standing ovation. The lecture was not printed until 1868, 2 years after Riemann was dead. He died at 39 of tuberculosis at Lake Maggiore in Italy, where he had gone for the milder air. He was working on a piece of mathematics when he stopped. There is a sad footnote that after his death his housekeeper tidied his study and disposed of a quantity of unpublished papers before anyone could stop her, and nobody knows what was in them. Meanwhile, his framework sat on the shelf, admired by specialists, useful for certain problems about surfaces, and otherwise regarded as an extremely elegant thing with no particular application. It was, in the phrase people use, mathematics in search of a use. 60 years of that. It is worth pausing on what he had actually built, because it is easy to hear it as merely abstract. He had built a language in which you can describe a space that is curved without there being anything for it to be curved inside of. That is the crucial move, and it is the direct inheritance of Gauss's ant. When we say the surface of the earth is curved, we picture it curving into the space around it. Riemann spaces do not need that. The curvature is written into the local distance rule, felt from the inside, measurable by an inhabitant, and requiring no outside at all. So if somebody one day wanted to suggest that the space we are standing in is itself curved, they would not have to explain what it is curved into. They would only have to say how distances behave near each point, and the whole thing would be well defined. Nobody wanted to say that in 1854. There was no reason to. Space was space, gravity was a force, the planets went round the sun, and everything worked. But the tools were now sitting there, complete, waiting, in a lecture almost nobody had read, by a shy young man who was already ill. Let that room empty out. The chairs are pushed back, the light is going in the windows, and the ideas are staying exactly where they were put, quite content to wait 60 years for someone to need them. Chapter 11. In 1907, a clerk in the Swiss Patent Office in Bern is sitting at his desk when a thought arrives that he will later describe as the happiest of his life. The clerk is Albert Einstein, and the thought is this: if a person were falling freely, they would not feel their own weight. That is all. It sounds almost too ordinary to matter. A man steps off a roof, and during the fall, he feels nothing pressing on him. His pockets fall with him. If he let go of a coin, it would hang beside his hand, not moving relative to him at all. For those few seconds, gravity has vanished from his private world. Turn that around, and it becomes strange. Imagine you wake in a sealed room with no windows, and you feel your normal weight underfoot. There are two possibilities. The room is sitting on the ground, on a planet, or the room is out in empty space, with no planet anywhere, being pulled steadily faster by some engine on the outside, so that the floor is rising to meet you. Einstein's claim is that there is no experiment you can perform inside that room to tell the difference. Gravity and acceleration are locally the same thing. Now shine a torch across that room, from one wall to the other. If the room is accelerating, the light takes a small amount of time to cross, and during that time the room has moved up a little. So, the beam are slightly lower on the far wall than it left. From inside, the light appears to have bent downward. But if you cannot tell the difference between acceleration and gravity, then light must bend in gravity too, and light travels in straight lines. Light is very nearly the definition of a straight line. So if light is bending, the honest thing to say is that something has happened to straight. It took Einstein 8 more years to turn that into a theory, and he was not able to do it alone, because he did not have the mathematics. He went to an old classmate from his student days in Zurich, a man named Marcel Grossmann, who had by then become a professor of geometry, and asked for help in something close to desperation. Grossmann went into the literature and came back with Riemann. There it was. Curved spaces described from the inside with a local rule for distance in any number of dimensions, worked out 60 years earlier by a shy young man who had died without seeing it used, and the further machinery Einstein needed had been developed in the meantime, largely by two Italian mathematicians, Gregorio Ricci Curbastro and Tullio Levi Civita, again for reasons that had nothing to do with physics. The years that followed were not tidy. Einstein took wrong turnings, published a version he had to abandon, argued with himself in public, and at one point was in a genuine race with the mathematician David Hilbert. In November 1915, he arrived at the final equations. What they say can be put, roughly, in a sentence that the physicist John Archibald Wheeler later made famous. Matter tells space how to curve, and curved space tells matter how to move, gravity. In this description stops being a force reaching across empty distance and pulling on things. The Earth does not tug on you. The Earth's mass puts a curvature into the geometry around it, and you, moving through that geometry, take the straightest available path. You are not being pulled down. You are going straight, in a space where straight bends toward the ground. You may have seen the picture of a heavy ball on a stretched rubber sheet with smaller balls rolling into the dip. It is a helpful image, and it is also gently dishonest, and it is worth knowing why. It uses gravity to explain gravity, since the balls only roll downhill because of the very thing being explained. And it leaves out the part that does most of the work, which is that it is not only space that curves, it is time as well. For a slowly moving object like you, sitting in a chair, almost all of what you experience as weight comes from the curvature in the time direction, from the fact that clocks nearer a mass run slightly slower than clocks further away. You fall because your straightest path through a curved space-time leads toward the region where time runs slow. Nobody is asking you to feel that. Let it wash past and let the pillow take the weight of your head. The theory came with predictions, and the first was already sitting in the records. The planet Mercury's orbit does not quite close on itself. Its nearest approach to the sun drifts slowly around, and after every known effect had been accounted for, a small stubborn residue remained that Newton's gravity could not explain. Einstein's equations produced that residue exactly, with nothing adjusted to fit. He said afterwards that it gave him palpitations. The second prediction was the bending of starlight. If light passes close by the sun's curvature should deflect it, so stars appearing near the sun's edge should look very slightly shifted out of place. You can only see stars near the sun during a total eclipse. So, in May 1919, 2 British expeditions went out, one to the island of Principe off West Africa under Arthur Stanley Eddington, and one to Sobral in Brazil. They photographed the star field around the eclipsed sun and compared it with photographs of the same stars at night months earlier. The announcement that November made Einstein famous overnight in newspapers all over the world. The honest footnote is that the 1919 measurements were at the edge of what those instruments could do. The error margins were large, and historians have argued for decades about how convincing the result really was at the time. What settled the matter was the repetition. Eclipse after eclipse, and later radio measurements of distant quasars, and today measurements so precise that the deflection is simply part of routine astronomy, and the bending turned out to be useful. A galaxy sitting between us and something further away acts as a lens, spreading the distant object's light into arcs, sometimes into a complete ring around the nearer galaxy. Astronomers now use those lenses as telescopes they did not have to build to see things that would otherwise be far too faint. The curvature also shows up in your pocket. The satellites used for navigation carry atomic clocks, and those clocks are further from the Earth's mass than you are, so they run faster, and they are also moving quickly, which slows them slightly. The two effects do not cancel. The net result is that a satellite clock gains something like 38 millionths of a second every day compared with a clock on the ground. If the system ignored that, the positions it reported would drift off by something like 10 kilometers a day. The correction is built in. Every time a phone tells you where you are, it is quietly assuming that space and time are curved, and in 2015, a pair of detectors in the United States registered a passing ripple in that curvature itself, a wave from two black holes spiraling into each other more than 1 billion years ago, stretching and squeezing the length of a 4-kilometer arm by less than the width of a proton. We can rest here. The prediction was made by a patent clerk with a piece of geometry borrowed from a dead man's lecture, and a century later, the universe is still answering yes. There is nothing more to do about that tonight, but lie still and let it be true. Chapter 12, after all that, the subject was in a slightly awkward position. There was Euclid's geometry, and spherical geometry, and hyperbolic geometry, and projective geometry from the painters, and Riemann's endlessly variable spaces, and various other systems that had grown up in corners. They all called themselves geometry. Nobody could say clearly what the word meant anymore. In 1872, a 23-year-old took up a professorship at Erlangen in Bavaria and answered the question in a way that has held ever since. Felix Klein said that a geometry is defined by what it refuses to let you change. Pick a collection of transformations, ways of moving or reshaping things. Then, the geometry belonging to those transformations is the study of whatever survives them untouched. If your allowed moves are slides, turns, and reflections, the rigid motions that a physical object can undergo, then lengths survive, angles survive, areas survive, and the geometry you get is Euclid's. If you also allow uniform scaling up and down, lengths stop meaning anything but angles and ratios survive, and you get the geometries of similar figures, which is the world of Thales, measuring a pyramid by its shadow. If you allow the flattening of a projection, distances and angles both go, and you are left with straightness and incidence, and that is Desargues. And if you allow any continuous stretching and bending at all, provided you never tear or glue, then almost everything goes, and what remains is topology. One idea, and the whole disordered family of geometries lines up as a single sequence, from the most restrictive to the most permissive, each one studying the residue that the previous freedoms could not destroy. That way of thinking spread far beyond geometry. Once you know to ask what stays the same while things change, you start finding invariance everywhere, and in the 20th century, that became the central habit of physics. The deepest example belongs to Emmy Noether, who worked at Göttingen in conditions that would have stopped almost anyone. She could not initially hold a paid position because she was a woman, and for years lectured under the name of David Hilbert, who had argued for her appointment with the observation that the University Senate was not a bathhouse. In 1918, she proved a result connecting symmetry to conservation. If the laws of physics do not change from one moment to the next, energy is conserved. If they do not change from one place to another, momentum is conserved. If they look the same in every direction, angular momentum is conserved. The great conservation laws, which had looked like separate facts about the world, turn out to be shadows of the world's symmetries. That is, Klein's idea, carried into physics, and it is still how theoretical physicists think. Now let us go and play at the loose end of Klein's sequence, where you are allowed to stretch anything, because it is the most restful part of the subject. The founding story is a small one about a town. In the Prussian city of Königsberg there was a river with 2 islands and 7 bridges connecting the islands and the 2 banks. A local pastime was to ask whether you could take a walk through the town, crossing every bridge exactly once. Nobody managed it. In 1736, Leonhard Euler, the most productive mathematician who has ever lived, explained why nobody ever would. His move was to throw away the map. The distances do not matter. The shapes of the islands do not matter. Which side of the street you walk on does not matter. All that matters is which pieces of land are joined to which, and how many bridges arrive at each. Shrink each landmass to a dot and each bridge to a line, and you are left with a diagram that a child could draw. Then he noticed the constraint. Every time your walk passes through a piece of land, it uses 1 bridge to arrive and 1 to leave, so bridges get used in pairs. A place with an odd number of bridges can therefore only be where you start or where you finish. You have 1 start and 1 finish, so you can afford at most 2 such places. In Königsberg, all 4 pieces of land had an odd number of bridges. The walk is impossible, and it was impossible before anyone tried. That is usually called the first result in topology, and it introduced the habit of asking what a shape is like when you stop caring about size. Dar found another one. Take any solid whose surface is like a sphere and count its corners, its edges, and its flat faces. Take the number of corners, subtract the edges, add the faces. You always get 2. A cube has 8 corners, 12 edges, and 6 faces. And 8 minus 12 is -4, plus 6 is 2. A pyramid on a square base has 5 corners, 8 edges, and 5 faces. And again you get 2. Squash it, stretch it, add bumps, and the number holds. But make the solid with a hole through it like a picture frame or a donut, and the same count gives 0. Every time. The number is not measuring size or shape. It is counting holes. That is what topology is, in the end. The study of the properties a shape keeps, when you are allowed to deform it as much as you like, so long as you never cut it and never join anything that was apart. In that world, a coffee cup and a donut are the same object, because the cup is a lump of material with a single hole through the handle, and you could knead one into the other without ever tearing it. You can hold the strangest object in the family with your own hands, and if you have a strip of paper somewhere near the bed, you could do it now, though there is no reason to get up. Take a long strip. Give one end a single half twist. Join the ends. What you have is the loop described in 1858 independently and within a few months of each other by August Ferdinand Mobius and by Johann Benedict Listing, who was the one who gave topology its name. It is Mobius whose name stuck to it. Run a finger along the surface, and you never lift it, and you come back to where you started, having covered what used to be both sides, because the band has only one side now. Draw a line down the middle all the way round, and the line meets itself. Cut along that line, and the band does not fall into two. It opens into one longer loop with a full twist in it. Klein himself has an object here too, a surface with no inside or outside at all, which cannot be built properly in three-dimensional space without passing through itself, and which glassblowers make anyway as beautiful useless bottles. The great question in this area was asked by Henri Poincaré in 1904 about how to recognize a three-dimensional sphere by its properties alone. It stayed open for almost a century and became one of the famous unsolved problems with a $1 million prize attached. In 2002 and 2003, a Russian mathematician named Grigory Perelman posted the solution to a public preprint website in 3 short papers, answered a few questions by email, declined the Fields Medal, declined the prize money, and withdrew from mathematics entirely. He is said to be living quietly in St. Petersburg. He has never explained himself at length, and he does not owe anybody an explanation. So let the paper loop sit on the bedside table with its single twist and its single side, being quietly impossible, asking nothing of you at all. Chapter 13. Everything we have looked at so far is smooth. Lines, circles, cones, spheres, surfaces that curve gently and behave well if you zoom in on them. Zoom in far enough on any of them, and they flatten out, which is the property that makes calculus work. Almost nothing in the world outside your window does that. Benoit Mandelbrot put it plainly. Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth. Zoom in on a coastline, and it does not flatten. You get more coastline with the same kind of raggedness as before, all the way down to the pebbles and then to the grains. The first person to catch this happening was not looking for geometry at all. Louis Fry Richardson was a British scientist who spent the later part of his life trying to find the statistical causes of war, and, while gathering data, he noticed that neighboring countries often reported wildly different figures for the length of the border they shared. Spain and Portugal disagreed by a large margin about the same line on the same map, so he went and measured. He took a pair of dividers, set them to a certain span, and walked them along a coastline on a map, counting steps. Then he made the span smaller and did it again. And what he found is that the smaller your dividers, the longer the coast becomes, because a shorter step follows inlets and headlands that a longer step simply cut across. The length does not settle down toward a true value. It keeps climbing in a steady, predictable way. Mandelbrot picked that up in a paper in 1967 with a title that is also the whole idea, asking how long the coast of Britain actually is. His answer is that the question is badly posed. A coastline does not have a length. It has a roughness, and the roughness can be measured. He gave these shapes a name in 1975, taking it from a Latin word for broken, and called them fractals. Here is one you can build in your head. Start with an equilateral triangle. Take the middle third of each side, and instead of the straight piece, put in a little peak, an outward point made of two segments, the same length as the piece you removed. You now have a 6-pointed star. Do the same thing again to every one of the 12 sides, and again. And forever, the result is the snowflake curve described by Helge von Koch in 1904. Every stage adds length and adds it in fixed proportion, so the perimeter grows without limit. The curve around the edge is infinitely long, and yet the whole figure sits comfortably inside a circle you could draw around the original triangle. So the area it encloses is finite, and in fact, rather modest. An infinite boundary around a finite garden. That curve is also the reason for the strangest word in this part of the subject, which is dimension. Think about how shapes behave when you double their scale. A straight line, doubled, is made of 2 copies of the original. A square, doubled, is made of 4 copies. A cube, doubled, contains 8. 1, 2, 3 copies of the doubling, and the exponent is the dimension. Now do it to the snowflake edge. If you scale a piece of it up by a factor of 3, you find it is made of 4 copies of the original piece. 4 copies at 3 times the scale. The exponent that answers, that is not a whole number. It comes out at about 1 1/4. So the curve is more than a line and less than a surface. It fills space more thoroughly than something one-dimensional, and not thoroughly enough to be 2. That is what roughness is, measured. You are welcome to drift off right here, in the middle of a snowflake. It will keep growing its edges without supervision. Once you know to look for this, it is everywhere, and the reason is usually that nature builds by repeating a process at smaller and smaller scales. A fern frond is made of leaflets shaped like the frond. Romanesco broccoli spirals into smaller spirals of the same form. River networks branch like the trees on their banks, and the trees branch like the blood vessels in your hand, and the airways in your lungs branch through many generations to pack a surface area the size of a room into a space the size of your chest. Branching is how you get a great deal of surface into very little volume, and roughness is what branching looks like from a distance. Film studios noticed the mountain ranges and coastlines in animated landscapes are frequently grown by a fractal rule rather than drawn, because a simple recipe repeated at many scales produces something the eye accepts as terrain. Now, the other half of this, which is the opposite temperament. Not roughness, but pattern, and the question of how shapes fit together to fill a floor. If you insist on identical regular polygons, only 3 of them will tile a flat surface with no gaps: triangles, squares, and hexagons. Nothing else fits. Bees use the hexagon, which uses the least wall material for a given amount of stored honey, a fact people suspected for 2,000 years, and which Thomas Hales finally proved in 1999. Ordinary tilings repeat. Slide the pattern along by the right amount and it lands on itself exactly. For a long time, it was assumed that any set of shapes that could tile the plane could tile it in some repeating way. In 1974, Roger Penrose found 2 simple 4-sided shapes, usually called the kite and the dart, which will cover a floor forever with no gaps and no overlaps, and which can never settle into a repeating pattern. The tiling has 5-fold symmetry, order without repetition, and any finite patch of it appears again and again elsewhere, while the whole is never quite the same, twice. That was a curiosity for 8 years, until a materials scientist named Dan Schechtman found a metal alloy whose atoms produced a diffraction pattern with 5-fold symmetry, which crystallography said was impossible. He was mocked for it and asked to leave his research group. He received a Nobel Prize for it in 2011. The open question that remained was whether a single shape could do it alone. One tile, no repeating pattern, nothing else needed. It was doubted for decades. In March 2023, a retired print technician in Yorkshire named David Smith, working with cutout cardboard shapes for the pleasure of it, found a 13-sided figure that looked as if it might. He wrote to people who could check. Together with Craig Kaplan, Joseph Samuel Myers, and Chaim Goodman Strauss, he proved that it does. They called it the hat. A few months later, the same group produced another one, the spectre, which works even if you forbid using mirror images. A question 2,000 years in the making, answered partly by a man at a kitchen table. One last pattern question, because it is the oldest practical one. How do you stack spheres most densely? Johannes Kepler said in 1611 that the answer is the way a greengrocer stacks oranges, and it took until 1998 for Thomas Hales to prove it, with a computer-assisted argument so long that the referees eventually gave up on being certain, and it had to be formally verified by machine years later. And in higher dimensions, the problem is mostly still open, except for 2 strange islands where it is now solved. Marina Vyazovska proved the answer in dimension 8 in 2016, and then in dimension 24 with 4 colleagues, using methods so unexpectedly clean that mathematicians describe reading them as a slightly unsettling pleasure. So, let the oranges stay stacked, and the snowflake keep adding its edges, and the hat go on covering its endless floor, without ever repeating itself all night, without needing anyone to watch. Chapter 14. We have come a long way from the mud, so let us finish by looking at where all of it ended up, and then at the largest question it can be asked. Start close to you. If there is a phone on the table beside you, everything on its face is geometry doing quiet work. The letters are described as curves defined by control points so that they can be drawn at any size without going ragged. Every photograph you have ever rotated or cropped, was passed through a small array of numbers that carried each coordinate to a new one. Every time you looked at a map, a curved patch of a planet was flattened onto a rectangle by a projection that had to decide what to sacrifice, exactly as Gauss showed it must. Medical scanners are geometry too. A scanner sends beams through the body from many angles and records only how much was absorbed along each straight path, and then reconstructs the interior from those shadows using a piece of mathematics worked out by Johann Riemann in 1917 for no practical purpose whatsoever. Half a century before there were machines that needed it. Chemists think in shapes constantly, because what a molecule does is largely a question of its form. A protein is a long chain that folds into a specific three-dimensional object, and its shape is what lets it fit against another molecule the way a key fits a lock. Predicting that folding was one of the hardest open problems in biology for 50 years. And recent progress on it, which has been considerable, is at heart a question about geometry. Engineers fold things. There is a family of creases named after Koryo Miura that lets a flat sheet collapse into a small packet and open again in one motion by pulling two corners, which is how solar panels have been folded for launch and opened in orbit. Origami, done seriously, is applied geometry, and it is being used for stents that expand inside arteries, and for telescope mirrors that have to leave Earth folded. Architects have always been in this business. Antoni Gaudi hung chains upside down from the ceiling of his workshop and photographed them, because a hanging chain takes the shape that carries pure tension, and flipping that curve over gives you an arch that carries pure compression. He let gravity design his columns and then turned the drawing the right way up. Even the way machines are now taught to recognize things is geometric. A photograph to a computer is a point in a space with an enormous number of directions, one for each pixel, and learning to tell a cat from a chair means finding the surfaces in that space that separate one region from another. Riemann's willingness to work in as many dimensions as the problem required stopped being a philosophical flourish and became an engineering necessity. Let all of that carry on without you. None of it needs your attention tonight. Now the last question, which is the one that has been standing at the back of the room since the parallel postulate first started causing trouble. If flat space, spherical space, and hyperbolic space are all consistent possibilities, which one are we living in? It is a measurable question, exactly as Riemann said it would be, and the measurement has been attempted on the largest available scale. The light left over from the early universe is still arriving, from every direction as a faint glow. It is very slightly uneven, hotter in some patches and cooler in others, and physics gives a good account of how large those patches ought to be in actual physical size. So we know roughly how big the patches are, and we know roughly how far away they are, and we can measure the angle they cover across the sky. That is a triangle. A very large one, with two sides reaching back most of the way to the beginning, and a base made of a hot patch of ancient light. And if space were curved, the angles would not come out the way flat geometry predicts. On a sphere, the patches would look larger than they should, In a hyperbolic space, they would look smaller. The measurements come out flat, as near to flat as the instruments can distinguish, with the remaining uncertainty small, which is a genuinely surprising result and worth being careful about, because flat is the knife edge between the other two, and there is no obvious reason for a universe to be balanced there, and there is an honest limit to what we can claim. We can only see out to a certain distance, because light has had only so long to travel. Everything we can measure is inside that horizon. A sphere large enough will look flat to anyone standing on a small enough patch of it, which is precisely why people believed the earth was flat for a very long time while walking around on a ball. So the fair statement is that the part of the universe we can survey is flat to within our ability to measure it, and that we cannot rule out a gentle curvature on a scale far larger than anything we will ever see. That is where the matter rests, and it may rest there permanently. What is not in doubt is that space is curved locally near anything heavy, in exactly the way Einstein described. The universe may be flat overall while being dimpled everywhere in detail, like a sheet with stones on it. So look at the whole shape of the night. It began with people standing in wet Nile silt with knotted rope, trying to work out where a field had been before the water took the markers away. Ordinary work, done by people whose names we do not have. From that came the idea that a statement could be proved rather than merely checked. From that came a book that stood for 2,000 years, with one uneasy sentence in its foundations. From centuries of failing to remove that sentence came the discovery that it could simply be refused, and that there are other worlds. From those other worlds came a language for describing curvature from the inside, without any outside. And from that language, waiting unused on a shelf for 60 years, came the explanation of why you are being held against your bed right now, not by a force pulling you down, by the shape of the space you are lying in. And the orange peel is the same fact in your hand, small enough to hold. It will not lie flat because its curvature belongs to it, and no map, and no gentleness, and no cleverness can talk it out of that. There is nothing left to do with any of this tonight. You do not have to remember the names, or the order they came in, or which theorem belonged to whom. The proofs will still be true in the morning, without your help, exactly as they were true before anyone found them. So let the rope lie coiled on the drying ground. Let the library stay dark and the scrolls stay shelved. Let the ant go on measuring its small circles, and the crocheted frill ruffle in its basket, and the paper loop keep its single side, and the snowflake keep growing its infinite edge around its quiet, finite garden. Let the satellites overhead keep their clocks a fraction ahead of yours, as they always do, all night, so that you are never lost. And let the whole flat, curved, patient shape of things hold you where you are. Good night.